Right now, at this very moment, something is approaching our sun from the depths of interstellar space. It arrived from a stellar system we cannot identify, traveling at 137,000 miles per hour. On July 1st, 2025, at 0432 Universal Time, the Atlas Survey Telescope in Chile detected it. By July 2nd, 3 independent observatories confirmed what should have been impossible. This object was not just passing through, it was active, releasing material, behaving like a comet at 6.5 astronomical units from the Sun, a distance where water ice remains frozen solid, where nothing should sublimate, where nothing should move. The Hubble Space Telescope imaged it on July 21st. The James Webb Space Telescope turned its infrared eyes toward it in August. The Zwicky Transient Facility found it in archival data stretching back to May 7th, 17 astronomical units out, already glowing, already outgassing. This is not how comets work. This is not how dead rocks drift. And here is what NASA will not tell you directly. The spectroscopic signature does not match any known cometary composition in our solar system. The ratio of carbon dioxide to water vapor is wrong. The activation distance is wrong. The dust production rate jumped from 5 kilograms per second to 30 kilograms per second in just 70 days as it fell toward perihelion. Its designation is 3I/Atlas. The third confirmed interstellar visitor in human history, and it is moving like it knows we are here. Let me ground this for you with institutional authority and hard measurement. The Atlas survey, funded by NASA and operated by the University of Hawaii Institute for Astronomy, detected the object using its twin 0.65-meter Schmidt telescopes. Within 18 hours, the Minor Planet Center had computed a preliminary orbit. The eccentricity came back at 6.143. For context, an eccentricity of 1.0 means an object is traveling exactly at solar escape velocity. Anything above 1 is hyperbolic. This object has an eccentricity over 6. Its velocity at infinity, the speed it will carry when it exits the Sun's gravitational influence entirely, is 60 kilometers per second. That is 216,000 kilometers per hour. That is not a speed you acquire by wandering. That is a speed you acquire by being ejected violently from a planetary system light years away, possibly billions of years ago. The inclination is 175.1 degrees, meaning it is coming at us nearly perpendicular to the plane of the solar system in retrograde motion from below the ecliptic. It is not following traffic, it is cutting across lanes. The perihelion, the closest approach to the Sun, was calculated for October 29, 2025 at 11:44 Universal Time, plus or minus 2 minutes, 1.356 astronomical units, inside the orbit of Mars. And here is the detail that should make you pause. NASA, ESA, and every major space agency with deep space assets has quietly redirected observation time. Hubble, Webb, TESS, SWIFT, SPASS, the Perseverance and Curiosity rovers on Mars, the Mars Reconnaissance Orbiter, Europa Clipper, the Lucy and Psyche missions, Parker Solar Probe, the Punch Constellation, SOHO, and ESA's JUICE spacecraft, currently on the far side of the Sunday, all of them turned toward 3I/Atlas. That is not a standard protocol for a comet. That is a protocol for something you do not understand and cannot afford to miss. Think of it this way. Imagine you are a lighthouse keeper, and every night for decades you have watched ships pass at predictable intervals, following known routes, signaling with familiar lights. Then one night, a ship appears on the horizon, traveling twice as fast as anything you have ever seen, glowing with colors that do not match any flag or beacon you recognize, cutting a course that intersects your reef at an angle no sane captain would choose. You do not panic. You watch. You record. You signal other lighthouses, but you also prepare, because that ship is not following the code, and you do not yet know if it is ignorance or intent. 3I/Atlas is that ship, and we are the lighthouse keepers, watching it close. Let me walk you through the escalation in discrete beats, with numbers that constrain the strangeness. First observation, dust production began at a heliocentric distance of at least 6.5 astronomical units, potentially as far out as 9 astronomical units. Water ice sublimates efficiently only inside 3 astronomical units. Carbon dioxide ice, however, begins to sublimate around 5 astronomical units, and carbon monoxide even farther out. The Zwicky Transient Facility prediscovery data shows that 3I/8LAS followed a brightening curve proportional to heliocentric distance to the negative 3.8 power. For comparison, 2I/Borisov, the only other confirmed interstellar comet, brightened at roughly -2 to -2.5. Dynamically old long-period comets in our own solar system, comets that have orbited the Sun many times and have been baked and altered by repeated solar heating, show brightening curves around -3 to -4. 3I/Atlas, an object that by definition has never encountered our Sun before, is behaving like a comet that has been here many times. Let that sink in. Second observation, the coma color. Multiple telescopes, including the Gemini North Telescope in Hawaii and instruments at the Instituto de Astrofísica de Canarias, reported that the coma surrounding the nucleus was distinctly reddish. That redness indicates dust grains, organic tholins, carbon-rich particles. The spectrum obtained by Gemini North's OSIRIS instrument and later refined by other observatories showed absorption and emission lines consistent with silicate dust, carbon compounds, and trace organics, but the ratios were off. The carbon dioxide to water ratio was higher than any comet observed at similar distances from the Sunday. Tony Santana Rose and colleagues, publishing in August 2025, noted that the coma grew redder throughout July, implying either a compositional shift in the material being released or a change in the surface layer being exposed as deeper ices sublimated. This is not how pristine interstellar objects are supposed to behave. 2I/Borisov was polarimetrically pristine, meaning its surface had been untouched by stellar radiation for potentially billions of years. 3I/Atlas is showing surface evolution consistent with an object that has been processed, either by its home star long ago or by something we have not accounted for. Third observation, anisotropic outgassing. Hubble's images from July 21st revealed a teardrop-shaped cocoon of dust extending preferentially toward the northwest at a position angle of 280 degrees, roughly 180 degrees from both the projected negative heliocentric velocity vector and the anti-solar direction. In plain language, the dust was not being pushed back by solar radiation pressure in the way tails normally form. It was jetting forward toward the Sun, asymmetrically, as if the nucleus were rotating and venting from a specific active region on its day side. That is common in comets, but the geometry here is unusual. A very faint tail was visible in the anti-solar direction, which radiation pressure could explain, but the dominant feature was the forward fan. The Hubble data, processed by a team led by David Jewett and Jane Liu, estimated a dust production rate of 30 kilograms per second at a heliocentric distance of 3.8 astronomical units, assuming 100 micron grains. That same team, using the Nordic Optical Telescope on July 2nd, reported the comet was clearly active and diffuse even when it was still over 4 astronomical units out. The progression is consistent with accelerating sublimation as it approaches perihelion, but the onset distance remains anomalous. Here is the terrifying part. The Transiting Exoplanet Survey satellite TESS observed 3I/Atlas before anyone knew it existed. TESS data from May 7th to June 3rd, 2025 showed the comet was already bright and active at 6.4 astronomical units. That is well beyond the distance where water drives cometary activity. The implication, published by researchers analyzing the TESS light curve, is that the activity is being driven by more volatile ices. Carbon monoxide, carbon dioxide, methane, ammonia, ices that sublimate at much lower temperatures, ices that suggest this object formed in the coldest, outermost regions of its birth system, far from its parent star, and has retained that volatile inventory across billions of years and trillions of kilometers of interstellar transit. But here is the contradiction. Objects that retain such pristine volatile loads should not show the kind of processed, reddened, compositionally evolved surface that 3I/Atlas is displaying. You cannot have it both ways. Either it is pristine and untouched, or it is old and processed. 3. I/Atlas appears to be both. Fourth observation, the trajectory. 3 I/Atlas is traveling on a hyperbolic orbit inclined 175 degrees to the ecliptic, which places it nearly in the plane of the solar system but moving retrograde. Its closest approach to Earth will occur when the comet is on the far side of the Sun, over 240 million kilometers away, 1.5 times the Earth-Sun distance. It poses zero collision risk, but it will pass Mars at a distance of 0.21 astronomical units, 31 million kilometers, on October 3, 2025. ESA's Mars Express and the ExoMars Trace Gas Orbiter will observe it with high-resolution cameras and spectrometers during that flyby. JUICE, though currently behind the Sun and using its high-gain antenna as a heat shield, will attempt observations in November and transmit data back in February 2026. These are not casual observations. These are forensic inspections, and the timing is not coincidental. The perihelion is October 29th, Mars flyby is October 3rd. That is a 26-day window when the comet will be at peak activity, outgassing at maximum rate, nucleus potentially fragmenting under thermal stress, and multiple spacecraft with direct sight lines. If something is going to happen, if this object is going to reveal its nature, it will be then. Now let me frame 3 scenarios, 3 interpretations of the data we have, presented not as conclusions but as hypotheses under test. Scenario 1. Benign interstellar vagrant. 3. I/Atlas is exactly what it appears to be, a comet ejected from a planetary system in the thin disk of the Milky Way, sometime in the past 1 to 2 billion years, drifting through the interstellar medium, bathed in cosmic rays, accumulating a surface crust of radiation-processed organics, and now encountering our Sun for the first time. The unusual chemistry reflects the different protoplanetary disk conditions of its home system. The early activation is due to higher concentrations of supervolatile ices. The anisotropic outgassing is due to an irregularly shaped nucleus with active regions concentrated on one hemisphere. The reddening coma is simply compositional heterogeneity, being revealed as layers sublimate away. In this scenario, we are witnessing an untouched sample of another star's planetary formation process, a Rosetta Stone in ice and dust. Every anomaly has a mundane explanation rooted in astrophysics we already understand. This is the scenario most scientists publicly favor, and for good reason. It requires no new physics, no extraordinary claims, no revision of our models. It is parsimonious, it is testable, it fits. Scenario 2, warning beacon or debris field marker. This is where we enter speculative territory, but bear with me because the data permits it. Suppose 3 I/Atlas is not natural in origin, or not entirely natural. Suppose it is a defunct probe, a leftover piece of ancient technology, or a deliberate marker placed in interstellar space by a civilization that ceased to exist millions of years ago. The high carbon dioxide to water ratio could indicate a manufactured or modified composition. The reddened surface could be ablative, shielding, or degraded structural material. The anisotropic outgassing could be venting from a ruptured containment system, not sublimating ice. The early activation at 9 astronomical units could be a thermal trigger or a passive reflective system responding to increasing solar flux. In this scenario, the object is not communicating, not signaling, not alive. It is simply decaying, a technological corpse following a ballistic trajectory set eons ago. We would not recognize it as artificial without close inspection because it has been eroded by micrometeorite impacts, cosmic radiation, and interstellar dust over timescales that obliterate surface features. This scenario is low probability, but it is not zero probability. We have exactly one data point for comparison, Oumuamua, which exhibited a non-gravitational acceleration inconsistent with outgassing, but also inconsistent with solar radiation pressure, and which tumbled in a way some researchers argued was more consistent with a thin, artificial structure than a natural rock. 3. I/Atlas is not showing Oumuamua-level weirdness, but it is showing enough oddities that this scenario cannot be dismissed without close-range investigation. Scenario 3. Active probe in diagnostic mode. This is the scenario that keeps me awake, not because I believe it, but because the data does not yet exclude it. Suppose 3I/Atlas is not defunct. Suppose it is operational, executing a mission profile designed to gather data on stellar systems it encounters. The early activation is not sublimation. It is a sensor array deploying or a power system spinning up, triggered by detection of our sun's spectral signature. The reddening coma is not dust. It is a cloud of microsensors dispersed to maximize sample volume, analyzing the solar wind composition, the interplanetary magnetic field, the radiation environment. The anisotropic outgassing is not random. It is a controlled release, jetting in specific directions to maintain attitude control or to position the sensor cloud optimally. The trajectory through the ecliptic plane is not coincidental. It is deliberate, designed to pass close to multiple planets, maximizing data return. In this scenario, we are not observing it. It is observing us. And here is the uncomfortable truth: we would not know. Our instruments are designed to detect natural phenomena. Spectroscopy tells us about molecules, not about whether those molecules are being released intentionally. Photometry tells us about brightness, not about whether that brightness is a beacon. Trajectory analysis tells us about gravity, not about whether microcorrections are being applied by a propulsion system too subtle for us to resolve. If an interstellar probe were designed to be indistinguishable from a comet, to camouflage itself as natural debris, we would need to get very, very close to know the difference. And we are not planning to get close. Let me give you an improbability stack, an accumulation of anomalies that individually are explainable, but collectively are harder to dismiss. Anomaly 1, activation distance. 9 astronomical units is far, but not impossible for carbon dioxide-driven activity. Probability, high. Anomaly 2, brightening curve consistent with dynamically old comets despite being a first-time visitor. Strange but explainable by high volatile content. Probability, medium to high. Anomaly 3, reddening coma, implying surface evolution inconsistent with pristine interstellar origin. Puzzling, but maybe it encountered its home star more recently than we think before ejection. Probability, medium. Anomaly 4, anisotropic outgassing geometry with forward jetting toward the Sunday. Unusual, but rotation and active region concentration can account for it. Probability, medium. Anomaly 5, high carbon dioxide to water ratio, unlike any known solar system comet. Odd but different protoplanetary disk chemistry is plausible. Probability, medium. Anomaly 6, trajectory inclined nearly perpendicular to the ecliptic, retrograde, passing within observation range of Mars during peak activity. Coincidental, but space is big and angles are random. Probability, low to medium. Now stack them. Each one has a mundane explanation. But when you combine them, when you ask what is the probability that all 6 anomalies occur together in a single object by chance, the product of probabilities starts to shrink. It is still far more likely that this is a natural object than an artificial one, but it is no longer overwhelmingly obvious, and that uncertainty, that residual doubt, is why every major space agency is watching. Now let me give you a countdown, a timeline of what to expect and what to watch for as 3I/Atlas approaches perihelion and beyond. October 3, 2025, Mars flyby at 0.21 astronomical units. ESA Mars Express and ExoMars Trace Gas Orbiter conduct multi-instrument observations. Watch for spectroscopic data on volatile composition, high-resolution imaging of the nucleus if possible, and any changes in outgassing rate or coma structure as the comet interacts with Mars's exosphere and magnetotail. October 29, 2025, perihelion at 1.356 astronomical units, 11:44 Universal Time, peak solar heating, maximum sublimation rate, highest probability of nucleus, fragmentation if structural integrity is low. Hubble and Webb will be imaging continuously. Watch for sudden brightness changes, breakup events, or asymmetric flares indicating focused outgassing. November 2025, Hubble conducts ultraviolet spectroscopy to measure sulfur to oxygen ratio in the coma and characterize gas emissions. Webb performs infrared spectroscopy to detect water, carbon monoxide, carbon dioxide, ammonia, methane, and complex organics. This will be the definitive compositional fingerprint. Watch for unexpected molecular signatures, isotopic ratios inconsistent with solar system norms, or emission lines that do not fit standard cometary models. December 2025. Webb conducts post-perihelion observations as the comet begins its outbound leg. Watch for changes in activity level. Does it continue outgassing symmetrically as it recedes, or does activity drop off sharply? Does the coma color shift? Does the dust production rate scale as expected with heliocentric distance, or does it plateau, suggesting a non-volatile energy source? February 2026. JUICE transmits data from its November observations, taken from a vantage point on the far side of the Sun, providing stereoscopic geometry with Earth-based telescopes. Watch for discrepancies in apparent position, brightness, or structure that could indicate resolved features on the nucleus or non-gravitational acceleration. March through December 2026. Long-term monitoring by Hubble, Webb, and ground-based observatories as 3I/Atlas exits the inner solar system. Watch for trajectory deviations. Any departure from the predicted hyperbolic orbit, any change in velocity not attributable to solar gravity and radiation pressure would be a red flag. Watch for late-stage activity. If outgassing continues beyond 5 astronomical units on the outbound leg, that would be inconsistent with solar heating and would require an alternative energy source. Watch for the object to dim and go quiescent, or watch for it to remain active, glowing faintly as it climbs back out toward interstellar space. And here is the observational trigger that would change everything. If, at any point, the object changes its trajectory in a way that cannot be explained by outgassing jets producing a rocket effect, if it maneuvers, if it corrects course, if it does anything that looks like a mid-flight adjustment, then we are no longer talking about a comet, we are talking about something else. The likelihood of that happening is extraordinarily low, but it is not zero, and that is why NASA has Parker Solar Probe, a spacecraft designed to study the Sun, tasked with observing 3I/Atlas. That is why the Perseverance and Curiosity rovers on Mars, machines built to study geology, are pointing their cameras skyward. That is why Europa Clipper, a mission to Jupiter's moon, is being asked to look at a comet. That is resource allocation for an object that is either far more interesting or far more important than its designation suggests. Let me close with the question that frames all of this. Are we alone? That question has haunted humanity since we first looked up and understood that the stars were other suns. For most of history, it was a philosophical question, a matter of belief or imagination, not something we could test. Then we developed radio telescopes and started listening. We found nothing. We developed space probes and started exploring. We found no life, no signals, no evidence. We developed exoplanet detection methods and discovered thousands of worlds, many inhabitable zones, many potentially capable of supporting life. But we still have no confirmation. And then, in 2017, we detected Oumuamua. In 2019, 2I/Borisov. In 2025, 3I/Atlas. 3 interstellar objects in 8 years. The Vera-C-Rubin Observatory, when it begins full operations, is expected to detect dozens per year. Interstellar space is not empty. It is filled with debris, ejecta from billions of planetary systems across the galaxy, fragments of worlds that never formed or worlds that were destroyed, and potentially, though rarely, artifacts. The question is no longer whether we will encounter interstellar objects. The question is whether we will recognize them when we do. 3I/Atlas is behaving strangely, not impossibly, not inexplicably, but strangely. And strangeness in science is data. It is a flag that says, pay attention, dig deeper, check your assumptions. I am not claiming this is an alien probe. I am not claiming NASA is hiding evidence. I am claiming that the object does not fit neatly into the boxes we have built to categorize comets, and that misfit demands scrutiny. We are in the era of interstellar astronomy now, the era where we can study the chemistry and physics of other star systems, not by building century-long starships, but by waiting for samples to come to us. 3I/ATLAS is one of those samples. It is a messenger from a place we cannot reach, carrying information encoded in its ice and dust and trajectory, and we have a closing window to decode that message before it vanishes back into the dark. So here is what I want you to do. Stay on the timeline. Subscribe to channels and feeds that will update you as the observational data comes in. Watch for the Mars flyby results in mid-October. Watch for the perihelion observations in late October. Watch for the Webb spectroscopy in November and December. Watch for the JUICE data drop in February. And watch for the long-term trajectory monitoring through 2026. If this is just a comet, we will see a predictable decay curve, a fading object following a ballistic arc back into interstellar space, and that will be fascinating in its own right because we will have learned about planetary formation conditions in another star system. But if it is something more, if there is a deviation, a signal, a behavior that crosses the line from natural to artificial, you will want to have been paying attention from the beginning. This is not a drill. This is not a movie. This is real-time science on the frontier of what we know. And here is the deeper question I want you to consider. If 3I/ATLAS were a probe, if it were designed by an intelligence that understood we would be watching, what would it do? Would it reveal itself immediately, broadcasting in radio frequencies we monitor, flashing lights and optical wavelengths we can see? Or would it stay quiet, passive, observing without announcing, gathering data without contact, because civilizations that survive long enough to build interstellar probes also learn to be cautious? Think about it. If you were sending a probe to another star system, would you program it to announce itself to any civilization it found, risking hostile response? Or would you program it to gather intelligence first, assess the technology level, the social stability, the potential threat, before deciding whether to make contact or simply report back? We assume that if aliens visited, they would want to talk to us. That assumption may be wrong. They may simply want to know about us. And a probe designed to know, to watch, to measure would look very much like a comet, because a comet is the perfect disguise. It is expected. It is natural. It explains the brightness, the outgassing, the trajectory. It arouses no suspicion until you look closely at the details and realize the details do not quite add up. I am not saying that is what 3I/ATLAS is. I am saying we do not yet have enough data to rule it out. And in the absence of definitive data, the intellectually honest position is to remain open to all possibilities that fit the observations, however unlikely some of those possibilities may seem. Science is not about believing, it is about testing. And right now, we are in the testing phase. The experiments are ongoing, the telescopes are watching, the data is accumulating, and in the coming months, we will know more. We will refine our models, we will constrain the chemistry, we will map the nucleus if we can resolve it. We will track the orbit to sub-meter precision. And if the data continues to fit a natural explanation, then we will publish papers on interstellar cometary composition and close the book on 3I/ATLAS as an interesting but ultimately mundane visitor. But if the data starts to diverge, if we see something that should not be there, a molecule that does not belong, a structure that is too regular, a trajectory correction that is too precise, then the book stays open, and the conversation changes. So I leave you with this. Is 3I/ATLAS just a comet from another star, or is it something more? The answer matters, not because it will validate science fiction fantasies or because it will upend our understanding of the universe overnight, but because it will tell us whether we are truly alone or whether the galaxy is watching. And if the galaxy is watching, if there are probes and sensors and quiet observers drifting through the interstellar medium, collecting data on star systems and planets and the emergence of life, then we need to know. We need to know because it changes everything about how we think of ourselves, our future, our place in the cosmos. We need to know because if we are not alone, if we are being observed, then every choice we make, every signal we send, every step we take into space is not happening in isolation. It is happening under scrutiny. That is the stakes. That is why this matters. Not because 3I/ATLAS is definitively artificial, but because it might be, and the only way to find out is to look closely, to measure carefully, to follow the data wherever it leads, and to be prepared for answers we did not expect. The universe is under no obligation to make sense to us, but it is under an obligation to be consistent with itself, and when we find inconsistencies, when we find objects that do not quite fit, that is where discovery lives. That is where the future opens up. So watch 3I/Atlas, watch it carefully, and ask yourself, as it climbs back toward the stars, whether it came here by accident or by design. The data will tell us, eventually, but in the meantime, think about what it means to live in a universe where the question is even possible. Think about what it means to have interstellar visitors arriving in our solar system with increasing frequency, carrying information we are only beginning to learn how to read. And think about what it means to be the generation that finally has the tools to answer the oldest question humanity has ever asked: are we alone? Or is contact not a matter of if, but of recognizing what is already here, drifting past us, silent and strange and waiting to be understood? That is the question, and 3I/Atlas might be the answer. Or it might just be the beginning of the search. Either way, we are watching, and the universe perhaps is watching back.